All right, hello and welcome to Monday Night Office Hours. Um, it's been, well, it's seven. It's been like 4.5 hours since lecture. I am. We don't have any pre-programmed stuff tonight, so I'm just here to answer your questions. I will take any and all of them. Oh, Stephanie, that is so so stinking sweet. It was a hard day, but it was a good day. When all is said and done, and I can definitely say actually part of what helped me was actually getting to lecture with you all this afternoon and getting to be here right now because there's something very cathartic about working where it takes your mind off the present, sets it on a different set of problems, and you can you can do some work in another area, exercise a different part of your brain, and it can help you get through. So thank you. It has been the second half of the day has definitely been better than the first half. Totally. So oh yeah. Yes, it absolutely does. It absolutely does. Yes. Yeah, I read it as mind, not mid, as well. What was I gonna say? I was gonna say something. Oh yeah, I can take any questions live. I'm gonna start going through my emails to see if anybody's sent any questions in. But as always, as always, I'll prioritize the live questions, and in the absence of any, I will hit up the email situation. Oh, let's see. Can we go over exercise 3? The question with how many mils of a... Okay, yeah, here. Let me... give me a second while I pull it up. Let's find the exercise. Hang on, Leanna, but if you can believe it or not, I'm still Still pulling it up. Let's see. There we go. Okay. And you said it was the question. Let's see. Sodium iodide and I2. All right, let's see. Consider the following reaction. How many milliliters of 0.5500 molar solution of sodium iodide are needed to produce 34.81 milligrams of iodine? Okay, what I'm going to do is I'm going to do this problem with different numbers. So I'm going to change the numbers around. And then that way I won't be betraying the answer, but you'll see how I did the calculation, and hopefully that'll be helpful. Okay, so we've got a reaction of COCl2. Okay, Tyrese, I will totally hit your question up after this guy in much the same way. So we're given this balanced chemical equation. It's I2 plus CO. All right, yep. There's our balanced chemical equation, and we're asked to find hang on just one second before we get there. We're given that we have, okay, so here's where I'm going to change the numbers. I'm going to go, I'm going to say we're going to use 0.60 to 0 molar solution of, not of that stuff, of sodium iodide. And we're told that we produce, and here I get to make up the number again. So I'm going to say that we make 58.30 milligrams of I2. And we're asked how many milliliters of this solution. All right, so this is what we're trying to find, is the milliliters of the solution. Now, when you think about it, milliliters is a volume, right? And molarity has an equation. Molarity equals moles of solute over liters. Now, milliliters and liters are different units, but liters is also a volume, right? So if we find the number of liters of this solution that we need, we just convert it to milliliters and we're good, right? So if we want to solve for liters, you take your equation, molarity equals moles over liters, and we're going to multiply both sides by our volume in liters so that liters cancel. Now we have an expression that says liters times molarity equals our number of moles. All right, and now if we want to solve for liters, we divide both sides by molarity. So we get a new equation that tells us that our volume in liters of this solution of sodium iodide is equal to our moles of sodium iodide over our molarity. Now we have this. We know what our molarity is because we were given that in the problem, right? Therefore, to find what our volume of the solution we need, we got to know how many moles. We got to know how many moles. And what we're given here is we're given our mass of iodine, all right? we're given our mass of iodine. So we're not, so we can take that mass in milligrams, convert it to grams so that we can find moles of I2. And then once we have moles of I2, we can use this balanced chemical equation and the mole to mole ratio to convert from moles of I2 to moles of sodium iodide. Once we have moles of sodium iodide, we're locked and loaded. So let's start with our mass of I2. We produce 58.30 milligrams. Now we know how to convert grams to moles, right? So before we can do that, we got to convert our milligrams to grams. Right, so we got milligrams right here, grams right here. 1 milligram is 10 to the negative third grams. So milligrams cancel. This leaves us with, oops, sorry, 0.05830 grams of I2. All right, that is our mass of iodine in grams. Now we need to take it and convert it to moles. So we're going to put grams in our denominator, moles in our numerator. And let's see, I got to bust out a periodic table. Let's see, iodine has a atomic mass of 126 point something, 0.9. 126.9 times 2, so we've got 2 of these in here. So that gives me a molecular weight of 253.80 grams in a mole. Grams of I2 cancels. Next, we're going to convert from moles of iodine to moles of sodium iodide because that is what we needed to solve for our volume. And this we get from the balanced chemical equation. 1 mole of iodine, if 1 mole of iodine is produced, that means 2 moles of sodium iodide reacted. And so now we're ready to crunch our numbers. We have 0.05830 divided by 253.8 times 2. Equals a 0.0004. Let's see, we can have 4 sig figs. So 4, 5, 9, 4, 2. I'm going to wait to round to the end. But I'm counting off those 4. And again, this is moles of sodium iodide. All right, now we can use the equation we developed. Our volume in liters will be equal to our number of moles, which we have here, 0.00045942 moles. And again, this has 4 sig figs. All over what's our volume? Oh, sorry, not our volume, our molarity. Our original molarity was 0.620. And molarity, whenever I punch it into a mathematical calculation, I break it up into the numerator and denominator because it helps me see what units cancel. So we take this quantity of moles, divide it by 0.6020, and the answer that I'm getting is 0.007632 liters. But then we weren't asked to calculate liters, we were asked to calculate milliliters, so we need one more unit conversion to go from liters to milliliters. 1 milliliter is 10 to the negative third liters. And dividing by 10 to the negative third is multiplying by 1,000. So we will need 0.7632 milliliters of a solution of this molarity to produce 58.30 milligrams. So that is the method that you need to use to calculate the volume in milliliters that you need to produce that many milligrams of I2. Okay, Tyrese, I remember your question. I remember writing your question. Let's see. Okay, so we're given... Let's see, this is another exercise 3 question. We are given a balanced chemical equation where we have 16 atoms of silver reacting with 1 molecule of S8 to produce 8 molecules of silver 1 sulfide. It's not called silver 1 because of the quantity of silver. It's called silver 1 because that's its oxidation state. All right, we're asked, what is the mass in grams of the excess reactant left over after 2 grams of each? So we're mixing, let's see, I think it's, well, okay. What I'm going to do is, again, just pick different units. I'm going to pick 1.87 grams of silver and 1.87 grams of S8. And here we're asked to find, so our question, actually, I'm going to open that on a new slide. So the question that we're being asked to solve is this. How many grams of, or that's faux, how many grams of excess reactant remain? All right. Now, the way you answer this question is as follows. So you've got some initial mass. And then you have the reacted mass, the amount consumed. And you take the amount that reacted, subtract it from your initial, and when you do that, you get your remaining mass, right? Or your excess. So this right here is the excess amount. Your initial mass in this problem were given. The reacted mass, you calculate this. You calculate it based on the limiting reactant. All right, so we've got to determine the limiting reactant and use that mass of limiting reactant to calculate how much will be consumed. Once we know that, we subtract it from our initial mass. All right, so that is the plan, that's the strategy. First, we got to find what our limiting reactant is, so we've got to do a limiting reactant calculation. 1.87 grams of silver. So first, we need to convert this to moles, and to do so, we take the atomic mass of silver, which is 196 point something. Oh, sorry, no, it's not. That's gold. Silver's 107. Okay, so you did the limiting excess thing. Awesome. Let's see, 107.87 grams. I'm just going to go ahead and finish the calculation for anybody who's watching and who may not know what to do. So our grams cancel. Next, we're going to go from moles of silver to moles of silver to sulfide. And here there are 16 moles of silver produce 8 moles of silver 1 sulfide. Moles of silver cancel. And this is where I'm going to stop because we don't actually need to know the grams of our product produced, or at least in this part. Oh, you know what? It asks this for the second part, so why not be thorough? So this will just be all of problem 9. So for that last step, we go moles of silver 1 sulfide. We convert it to grams. So 107.87 times 2 plus 32.07. 1.87 divided by 107, divided by 107.87 times 8 divided by 16 times 247.81. All right, so for silver, based on this mass, let's see, I can keep 3 sig figs. This would be 2.15 grams of silver sulfide. Then we repeat this for S8. So first we convert to grams, so 32.07 times 8. That'll be our molecular mass, so 256.56 grams of S8. This is moles of S8. Grams cancel. Next we convert moles of S8 to moles of silver 2 sulfide, or silver 1 sulfide, excuse me. 1 mole of S8 produces 8 moles of the product. Moles of S8 cancel. And then in our final step, we take moles of silver 1 sulfide and convert it to grams. All right, so crunching these numbers, 1.87 divided by 256.56 times 8 times 247.81. Oh, this is way huger. So this could potentially produce 14.4 grams. So that means that the first one is our theoretical yield, and silver is our limiting reactant. All right, and the reason why this was important is because now that we know silver is the limiting reactant, we can calculate the grams of S8 that will be consumed. So the S8 grams of S8 that's consumed, we calculate like this. We go start with our mass of limiting reactant, convert it to moles. So 107.87 grams of silver in 1 mole. Times, now we got to convert from moles of silver to moles of S8. And this is a 16:1 ratio from the balanced chemical equation. Let me cancel some units. Then we need to convert from moles of S8 to grams. That was 256 something. Let's go 32.07 times 8. Yeah. 256.56 grams. .87 divided by 107.87 divided by 16 times 256.56. All right, this comes out to be point, let's see, 278 grams. And the important thing to remember, what we just calculated, is this is the amount that reacts. Oops. All right, that is the mass that reacted. So now we can take our initial quantity of S8, which was, let me switch to black here, 1.87 grams, and then the amount that reacted away, we're going to subtract. So this is going to be minus 0.278 grams, and the difference here will be the amount in excess. So 1.87 minus 0.278. My calculator is telling me the answer is 1.592. However, sig figs wise, I've got to round to the hundredths place and 2 rounds down. So my final answer would be 1.59 grams of S8 are in excess. All right, okay. Sammy and Kate, thank you so much for your kind words. It's definitely been a better second half of the day than it was the first half, and just thank you for being kind. I appreciate that a whole lot. Okay, let's see, Kate, you've got a question. There's one chapter 5 lecture example without n given. It asked for the density. Oh. Okay, yeah. Let's see. Okay, and then additionally during the 10.5. Oh, okay, so I'm gonna answer your second question first, because it's more just kind of general. And and then I'll hit your first question second. So density, not density, density. Density is equal to the mass of a substance. It's a ratio of the mass of the substance to the volume that substance occupies. And the most common density unit that we deal with in chemistry is definitely grams per milliliter, but the reality is that this numerator could be any mass unit. There we go. You could have any mass unit is in the numerator as long as it is a unit for mass, and in the denominator you could have any volume unit. And typically, so gases are not very dense. And we know this intuitively, right? Like gases aren't heavy things. They're light, they're airy, they're Aang, right? From The Last Airbender. And so because they're not very dense, substances, they tend to be, the density of gases tend to be measured in grams per liter. Because when you take grams per milliliter of a gas, the numbers get very, very small. They kind of look more normal when they're measured in grams per liter. They don't have to, and specific problems will say, if you're asked to find the density, it'll say find the density in grams per milliliter or find the density in grams per liter. So that can vary problem to problem, just depending upon what they ask for. So grams per liter, totally solid unit for density. Grams per milliliter, also totally solid, because as long as you have a volume unit in this denominator, you're going to be totally fine. All right. Okay. So that's why we solve for the density in grams per liter there. Okay. Now let's look at. Okay, you said there was an example in. Awesome. You are totally welcome. Let's see. You said that it asked for the density of nitrogen gas at STP. Okay. Okay, here. Hang on one second. I'm going to pull out a scratch piece of paper. I think I know the problem that you're talking about. Leanne, I totally can. Once I finish answering Kate's question, I will totally bump over to yours. Okay, hang on. Okay, yeah. Kate, here's the cool thing. So let's take a look at that example here. What is the density of nitrogen gas at STP? All right, now we know that STP is standard temperature and pressure, which standard pressure is 1.00 atmospheres, and standard temperature is 273.5 0.15 Kelvin. Okay, sorry about that. Okay, so is this still? Let's do that. There we go. Okay, so we know our pressure and our temperature, and when you look at, so there's a fun trick to this problem. When you look at the ideal gas law, the only information that we've been given in this problem is we've been given our pressure and our temperature. And of course, we always know R. All right? Now, I'm going to do a fun algebraic trick with the ideal gas law. So, check this out. I'm just going to rearrange it. I'm going to multiply both sides by 1 over R times T times V. All right? Both sides of this equation. So, R times T times V, nothing changes. Nothing changes except volume cancels from the left side and RT cancels from the right side. All right. This gives us N over V is equal to P over R times T. Now N is moles and V is liters. So this is equal to moles over liters. Now let me ask you, what is density? Density is grams over a volume, could be liters. The only difference between density and what we have here is that density has grams in the numerator, whereas right now we have moles in the numerator. And let me ask you a question. Can you convert from moles to grams for a sample of N2? You totally can, right? You use the molecular mass. So check this out. If you punch in P, R, and T, pressure is 1.00 atmospheres. R is 0.08206. It's good, right? It's really cool. Liter atmospheres per mole Kelvin. And then with temperature, it's 273.15 K. And when you look at how all of these things cancel, atmospheres takes care of atmospheres, Kelvin takes care of Kelvin. And so we get 1 divided by 0.08206, also divided by 273.15. So this comes out to be 0.044636. We can only keep 3 sig figs here. But this is, I'm gonna bump it over to a new slide. Oops. 0.044636. These are moles of N2 over liters. And this has 3 sig figs, as we said before. So all we need to do to find our density is just convert moles to grams. And 1 mole of N2 gas has a mass of 28.02 grams. All right. And so now we just crunch our numbers. So N2 gas at STP will have a density of 1.25 grams per liter. So that is how you can handle that problem without having to know how many moles of N2 gas are present in the sample. So that's a fun problem. Okay, Leanna, you have a question on exercise 3, potassium chromate. Let's... Totally. Well, that is exactly what office hours are for. Okay. Okay, Leanna, let's see. Okay, the percent of potassium chromate. Let's see. Oh, percent yield of potassium chromate. Okay. That's the limiting reactant. Calculate the percent yield. Okay, let's see. Okay. So let's take a look. So this is, so we're given a balanced chemical equation, which I'm going to throw up here. Oh, this is quite a chemical reaction. Let's see. Four. Angelina, I see your question. I'll hit it up once I finish working this problem. But I just want you to know that you're seen, and I'm totally not ignoring you. But I'll do this one first, and then you're next. Okay. So, with this experiment, so they want us to calculate. They want to know what is the percent yield of potassium chromate. And percent yield has an equation, right? It equals the actual yield divided by the theoretical yield times 100. And in this problem, here's what's given. Actually, I'm going to scoot this equation down just a little bit. So what they give us is they tell us in the problem what the actual yield is. So since we know the actual yield, all we have to do is calculate what the theoretical is. But here's the thing. They give us the kilograms of each reactant. So we have to do a limiting reactant calculation once with each of these reactants, whichever one produces could potentially produce the smallest amount, that is our theoretical yield, and that is what we plug in to the denominator of this expression. So to get there, and I'm going to use different numbers, all right, than they do in this problem. So I'm going to change the numbers ever so slightly, but we'll be able to do the calculation all the same. So I'm going to say that we're given 288 kilograms of the first thing, which goes by the name of chromite. That's just a common name. That's not an official name. I'm going to say that we're given 356 kilograms of potassium carbonate, and that we're given 94.0 kilograms of oxygen. So we need to do this calculation 3 times. We'll start with kilograms of chromite. First, we need to convert our kilograms to grams. So 1 kilogram is 1,000 grams. That is our first unit conversion. Second, we need to convert grams to moles. And this is going to take a little legwork. So iron is like 50 something. I want to say 55. 55.85. Chromium is close to iron. Oh, yes, it is. It is 52. Let's see, 0.00. And we have 2 of them. And oxygen is 16.00. So 52 times 2 plus 16 times 4 plus 55.85. Comes out to 223.85 grams in a mole. Next, we convert from moles of chromite to moles of potassium chromate. And the mole-to-mole ratio comes from our balanced chemical equation. 4 moles of chromite produce 8 moles of potassium chromate. Finally, we convert from moles of potassium chromate to grams. And potassium is around 40. It's like 39 something. 39.10. Chromium, as we already know, is 52.00. Oxygen is 16. And we are dealing with 4 oxygens and 2 potassiums. So 39.1 times 2 plus 52 plus 64 is 194.20. So that's 194.20 grams of potassium chromate. Sorry, we're a little scrunched there on the end of the screen. And now we can calculate what might be our theoretical yield. We won't know until we do this 2 more times. So 288 times 1,000 divided by 223.85 times 8 divided by 4 times 194.2. And this number is so outrageously large. I'm just going to crunch this one more time. 288 times 1,000 divided by 223.85 times 8 divided by 4 times 194.2. Okay, I got the same number both times. I doubt this will be the limiting reactant, but we'll see. This comes out to be, we can keep 499,706 grams of potassium chromate. We can only keep 3 sig figs. I'm not going to round my sig figs right now because this is not the end of our calculation. But I am going to put those marks there. Let's do this calculation for potassium carbonate, where we start with 356 kilograms. I have a feeling it's going to be oxygen, but we'll see. It might not. We don't know. That's why we're doing it. So we begin by converting from kilograms to grams. Next, we convert from grams of potassium carbonate to moles. And potassium 39.1, carbon 12.01, oxygen 16. And we have 2 potassium, 4 oxygen, 39.1 times 2 plus 64 plus 12.01 is 154.21 grams in a mole. Next, we got to convert from moles of potassium carbonate to moles of potassium chromate. And the unit conversion here comes out of our balanced chemical equation. It's a 1-to-1, right? 8 moles of potassium carbonate produce 8 moles of potassium chromate. Finally, in our last step, I was a bunch more careful with the space this time. 1 mole of potassium chromate contains 194.20 grams of potassium chromate. All right, 356 times 1,000 divided by 154.21 times 8 divided by 8 times 194.2. This number also comes out to be huge. It's 448, 318 grams potassium chromate. So far, that's lower than the first number, so we know the first number isn't the theoretical yield. Let's do our third and final. 94.0 kilograms of oxygen. So we have 1 kilogram in the denominator, 1,000 grams in the numerator, because we got to convert kilograms to grams. Next, we need to convert from grams of oxygen to moles. There are 32.00 grams of oxygen and 1 mole of oxygen. We next go from moles of oxygen to moles of potassium chromate. And this we get from the balanced chemical equation. It is a 7 to 8 ratio. Oops. There we go. Apologies for the shift in the screen that you're about to see. It is only temporary. Next, we convert from moles of potassium chromate to grams. All right, and our mass molecular mass of potassium chromate is 194.20 grams per mole. At long last, we are ready to crunch these numbers. We got 94 times 1,000 divided by 32 times 8 divided by 7 times 194.2. Dang, that number's huge. I'm just going to double check. 94 times 1,000 divided by 32 times 8 divided by 7 times 194.2. All right, and shoot, I thought this was going to be the smallest number, and look, turns out it is the largest of them all. Sorry, that's not kilograms, that's grams. So our limiting reactant then, that would have 3 sig figs. Our limiting reactant is potassium chromate. This is our theoretical yield. All right, that is our theoretical yield. So, bumping over to a new slide, percent yield is actual over theoretical. There we go. And we are given our actual, which is 194 kilograms. Our theoretical, we just calculated as being, hang on, let me pull it up real quick. We just calculated our theoretical as being 448,318 grams. Now, we've got a problem here. Well, first, 3 sig figs in the denominator, but the problem is grams and kilograms don't cancel. So before we can crunch these numbers, we actually need to do one last unit conversion. We're going to take 448,318 grams, and remember this has 3 sig figs, and convert this to kilograms. Grams go in the denominator, kilograms in the numerator. 1 kilogram is 1,000 grams. So this will be 448.318 kilograms. So let's rewrite this. 194 kilograms is our actual over a theoretical 448.318 kilograms. Again, 3 sig figs in our denominator. Times 100. So, crunching our numbers. 194 divided by 448.318 times 100. This, by the way, I used different numbers than the problem, so the percent yield that I calculated is not available as an answer because it's not a possible answer. So don't freak out if you're comparing this to exercise 3. Percent yield is 43.3%. All right, so that is how you do that problem. It's long. There's some extra unit conversion steps because of the use of kilograms, but that's how you do it. All right, Angelina, you have been super patient. Thank you for waiting. Let's see what your question is. In the example earlier today surrounding the temperature decrease in the balloon system was endothermic. So Angelina, that is an excellent question. And I just should make the distinction that energy is conserved. Energy is conserved. The decrease in temperature, however, sorry. It's been a long day. It was a coincidence. That will not always be the case, especially since we were looking in that instance at work, which doesn't have to track with Q, which is thermal energy. So yeah. Okay, here, hang on. Okay, sorry about that. My kids are watching apparently hilarious YouTube videos. But they're gonna relocate. Okay. All right, I'm gonna. Oh, let's see. So, just because there was a change in temperature. Okay. Well, Angelina, great question. So changes in temperature. I should say changes in temperature do correlate to changes in thermal energy. However, in that problem, We were calculating the energy transferred through work, which does not have to correlate. So, thermal changes in temperature will correspond to changes in thermal energy 100% of the time. That being said, in that problem, we were calculating the energy transferred through work, which does not necessarily correlate with changes in thermal energy. So energy transferred through work functions independent from thermal energy, and sometimes they track the same way, but sometimes they're different. And so that's the point I was making. But you are correct in your observation that changes in temperature do correlate to changes in thermal energy. It's just, again, that problem, we weren't looking at thermal energy, we were looking at energy transferred through work. Angelina, you are so totally welcome. Okay, Angelina, so it's the opposite true. Q cannot change without the temperature changing. Yes. That is 100% correct. Or, I guess I just wrote 105. 100% correct. Also, is there a way work can be done by liquids and solids in a chemistry context like we did with gases? Angelina, the answer is yes. They can. It is possible, but the thing is, it's so rare, and those circumstances are so special that they're generally ignored. And it's mostly because liquids and solids, though they do, we know that they experience some changes in volume. They tend to be so small that they're ignorable. And we actually do most of our thermodynamic work as chemists under the assumption that volume isn't changing unless we're looking at gases, because the amount that the volume has to change is so large for it to make a difference energetically that that it's actually a solid assumption that changes in volume won't be involved in energy transfer processes for most circumstances that chemists deal with. It's not that it doesn't happen, but the instances where the amount of energy transferred through work when you're dealing with a liquid or a solid is so few and far between, it just doesn't matter most of the time. So can it happen? Totally. But to see it happen, you're going to have to get into some very, very, very specialized stuff. So specialized that it's beyond the scope of first semester Gen Chem. But that is an excellent, excellent question. All right, let's see. Oh, and Angelina, actually, I just I'm looking through my emails and I saw your office hour question. Awesome. You are so very welcome. All right, and so hang on. Message. Okay, 4.129. Wait, that's not that one. There we go. Awesome. Okay, I'm looking at the questions you sent over. Okay, so let's see. So we're given a balanced chemical equation. Let's start this over. So our balanced chemical equation has ammonium sulfate reacting with sodium hydroxide producing sodium sulfate, liquid water, and ammonia. All right. And we're told in this problem that we have 0.608 grams of sodium sulfate. It's analyzed for nitrogen by heating with sodium hydroxide. The ammonia was collected in, okay, cool. We're told that it was collected in a 46.3 milliliter okay. Sorry, hang on. I thought I knew where this was going, and then it took a surprise twist. So we're told that the ammonia produced by this reaction, so this ammonia was taken and reacted with HCl. To produce ammonium chloride. All right, and that this solution was titrated. Oh, wow. Okay, motors acted in 46. This solution was titrated for excess HCl. Okay, so with, okay. And then, okay, so get this. So the ammonia is then taken and reacted with a solution of 0.213 molar hydrochloric acid, and it's dumped just into 46.3 milliliters of it. And then this is the this is where things get intense. Here, hang on. I need to bust out a few colors here. Hang on. Just grabbing all the colors that I need. Okay, there we go. Okay. And we'll add that right there. Okay. All right, so get this. Then, in the second reaction, this, which is an excess, is taken. Oh, I need a bigger eraser. Oh, shoot, that's right. Okay, so this HCl is in excess, and that HCl is taken and reacted sodium hydroxide to produce water and salt. And the amount that's used is we use 0.128. Yeah, totally. Angelina, this thing is intense. 0.128 molar sodium hydroxide, and 44.3 milliliters are used. All right, so here, get this. And what are they asking? This problem's so long that you can't even remember. They are asking this question. What is the percentage of nitrogen in the fertilizer? Based on these calculations, though, not based on the chemical formula. All right, so here's the deal. The percentage of nitrogen, and this is going to be a mass percent, is the grams of nitrogen, which we don't know, over the total mass, 0.608 grams times 100. All right. I'm going to change the color of this thing down here. All right, so that is what we're after. Percent of nitrogen. Okay, now I'm going to lay out conceptually where we're going. This will tell us the excess of HCl. These two things right here will give us the total HCl. All right. Now, if we take the difference between total HCl and excess HCl, this will give us the moles of NH3 produced. Technically, it gives us, it's the moles of HCl that reacted with NH3. But you can see here that this is a 1-to-1 mole ratio. So it, for all intents and purposes, gives us the moles of NH3. All right. And what we need are the grams of NH3. So once we have the moles of NH3, we convert the moles of NH3 to moles of nitrogen, and then we convert it to grams of nitrogen, and then we take this little box, plug it in here, and that'll give us the percentage. All right, so this problem is obnoxiously long and hard. And here's the deal. This is longer and harder than any single problem I would put on a test. So, if we can do it, that means we're all set, right? That means we should be, this is great preparation for the test, because this is something that's even too gnarly or gnarlier than I would put on it. Okay. So with that kind of outline, now let's get down to working this problem through. All right. So, step number 1. Let's find our total moles. Of HCl. Total moles of HCl. Do you have to get the moles of ammonium sulfate? You don't have to, actually, because they just want to know the percentage of nitrogen in the ammonium sulfate, and that percentage will be a mass, and so we know our total mass of ammonium sulfate, so we actually don't have to do any sort of manipulation of that volume, or not that volume, that quantity. And that might just be the one piece of good news that we have gotten in this problem. Okay, so let's see. Oh wait, where did the problem go? There we go. That's that guy. Okay. Okay, so let's find our total moles of HCl. We have 0.213, and now molarity is moles of solute over liters of solvent, and we need to multiply this by our volume. Now they give us our volume in milliliters. To do this calculation, however, we need to convert it to liters. That way everything cancels. So that is our volume in liters. Cancel here, cancel here. This gives us our total moles of HCl is, let's see, 0.213 times 0.0463. And this is equal to 0.00986 moles of HCl. Now, let's find the excess HCl. All right, our excess quantity of HCl, which we can find with the amount of sodium hydroxide that reacts. So 0.128. Now technically these are moles of sodium hydroxide per liter times our volume of sodium hydroxide converted to liters, 0.0443. Now why did I say this is how we find excess HCl? Well, because we also have a balanced chemical equation where we can convert moles of NaOH to moles of HCl, and in that balanced chemical equation we see that this is a 1-to-1 molar ratio. So it does indeed give us our moles of HCl. If we crunch the numbers, 0.128 times 0.0443 equals 0.00567 moles of HCl. That's the amount in excess. Now we can take the difference. So we take our total, which is 0.00986 moles of HCl minus 0.00567 moles of HCl. That's the amount in excess. So the moles of HCl that reacted are the difference between these two numbers. So 0.00986 minus 0.00567. And this is 0.00419 moles of HCl. And these are the moles of HCl that reacted with ammonia. So we can convert these to find out how many moles of ammonia were produced. And then we can convert from moles of NH3 to moles of nitrogen, just nitrogen, because the ratio here is 1 mole of NH3 has 1 mole of nitrogen atoms in it. So this is a 1-to-1 mole ratio. And then last but not least, we convert from moles of nitrogen, 14.01 grams. All right, so we take our moles of HCl times 1 divided by 1 times 1 divided by 1 times 14.01 gives us a mass of 0.0587 grams of nitrogen And now we can calculate our percentage. Because our percent mass of nitrogen is the grams of nitrogen, 0.0587, over the total mass of fertilizer, which in this problem is 0.608 times 100. Keeping it to 3 sig figs, this comes out to be 9.65%. Again, this problem obnoxiously long. Yeah. Totally. That first equation was just extra unneeded information. I think they were giving it to you so you could like see this is why we're doing all these acid-base reactions, because ammonia is a base, so then we take that, react it with an acid, react the excess acid away, so you could kind of visualize it. At least that's my guess why they did it, but you don't actually need it for solving this problem. Let's see. Okay, and then you wanted to see 141 as well. Let's take a look. All right, 141. A metal was converted into a sulfate. Then a solution of the sulfate was treated with barium chloride. To give barium sulfite crystals, which were filtered off. If 1.2 grams of the metal gave 6.026 grams of barium sulfate, what is the atomic weight of the metal? Oh, dude! Dude, it is my pleasure. Yeah, totally. This next problem is not as gnarly. That first one was a doozy though. Not gonna lie. All right, so check this out. So they give us a ton of information. They give us a balanced chemical equation. We've got this metal sulfate situation right here, which is aqueous, plus barium chloride, also aqueous, producing this metal chloride and barium sulfate, which is a solid. All right. Okay. Now, they tell us that 1.200 grams wait, hang on. Okay, we got to read this carefully. They say that 1.200 grams of just the metal by itself, when it's converted to the sulfate, and then it's treated with barium chloride to get barium sulfate crystals. So if we start with 1.200 grams of the metal, we get 6.026 grams of barium sulfate. And then we're asked to find what is the molecular weight of the metal, of this metal. Now, molecular weight has an equation, right? Molecular weight is equal to grams over moles. And check this out. We've actually been given grams of metal right here. So all we need to do is we need to find the moles of the metal that reacted. To do that, we're going to take our grams of barium sulfate, convert it to moles, and then use the mole-to-mole ratio, because 3 moles of barium sulfate are produced from 1 mole of this metal sulfate, and then 1 mole of the metal sulfate actually contains 2 moles of that metal. So we're going to do a grams to moles, moles to moles, and then moles to different moles calculation to figure out how many moles of metal there are, and that is the denominator that we're looking for here. All right, so that's our game plan. Let's begin crunching our numbers. So we've got 6.026 grams BaSO4. And we're going to multiply this by its molecular weight. Now we've got to look some stuff up. Barium has an atomic mass of wow, it's huge, 137.33. Sulfur, 32.07. Oxygen is 16. But we got 4 of them. So 137.33 plus 32.07 plus 16 is 185.40 grams of barium sulfate is the mass of 1 mole of barium sulfate. Next, we use our balanced chemical equation to convert moles of barium sulfate to moles of our metal sulfate, which we don't know what that metal is. And this is a 3 to 1 mole ratio. 3 moles of barium sulfate are produced by 1 mole of the metal sulfate. Finally, we need a unit conversion that'll take us from moles of our metal sulfate to just moles of metal. And when you look at the you get this unit conversion from the from the chemical formula. Because 1 mole of this molecule contains 2 moles of that metal. So this is a 1 to 2 molar ratio. Now you'll notice that grams of barium sulfate cancel. Moles of barium sulfate cancels. And then moles of the metal sulfate cancels, leaving us with moles of metal. So let's crunch these numbers. 6.026 divided by 185.4 times 1 divided by 3 times 2. So I'm getting 0.021, let's see, 4 sig figs, 7 moles of metal. Now, for for our molecular weight, let's get this in black. For our molecular weight, we take our mass, 1.200 grams, over 0.02167 moles. And we punch in our numbers to get a molecular weight of 55.38 grams per mole. So again, in this problem, you can see the key to really solving it was writing out the equation for molecular weight. And that kind of gave us the roadmap to solving this problem, which is kind of a common theme in this class. Often the algebraic expressions for the quantities that we're using, interacting with, become the roadmap to solving the problem. All right, let's see. Angelina, you are so totally welcome. Okay, Leanna, let me see. Exercise 3, the acrylonitrile problem, asking for mass in grams being produced. Okay, let me take a look. So you're talking, okay, good. Yeah, totally. That's all you have to do for that part of the problem. So you didn't even need me in the first place. Anytime, Leanna. Oh, Andrew, let me see. I just saw your question. Ah. Totally. I totally am going to do packet number 2 for exam 2, just like I did for exam 1. Ah, yeah. Yeah, they totally were rewrites of problems that appeared on the test. Dude, for sure, time does make a big difference, which is why, like, honestly, whenever you're in a time situation, and this is true, not just for chemistry tests, any test. Yeah, dude, you have a good night too. Something to keep in mind whenever you're being tested, always look for the problems that are quick and easy, bang those out first, and save the harder problems for the end. It's more efficient. You'll lock down the points you can for sure get, and you'll have more time to work the harder problems rather than being crunched for time on easier ones. It's a good test taking strategy. All right, Rin, let's see. Okay, question. In exercise 3, there's a series of questions about TNT. Yes. Okay. Rin, that is a very difficult balancing problem. And you may be relieved to know that this is actually harder than any problem that I would put on the test. So this example is kind of a cut above. I would never give this to you guys under a timed situation. But that's also why exercise 3 is a great opportunity to do a problem of this caliber because there isn't the time constraint. But needless to say, so we've got TNT, which is C7H5 N3O6. Stephanie, we totally can. I'm gonna work this problem and then I'll bounce to yours. Your question. Okay, so we've got TNT reacting with oxygen to produce carbon dioxide and water. All right, so carbon. Wait, hang on. Oh, and two gas. I was like, wait, something's not right here. Hold up. And N2. HNO. All right, on our reactant side, 7 carbon, 5 hydrogen, 3 nitrogen, 6 oxygen. On our product side, 1 carbon, 2 hydrogen, 2 nitrogen, and then 2 oxygen from CO2, 1 from water. Okay, now, Rin, as I said, this is a challenge level that I would not put on a timed situation. There's a really subtle trick to solving this problem. I didn't go over this when I taught in lecture how to balance chemical equations, just because it's so you come across a reaction like this so infrequently that it's not worth spending time. Plus, it always makes for some interesting office hour questions around this time in the semester. So one thing you'll notice is you have 2 nitrogen on the reactant side, on the product side, and 3 on the reactant side. All right, and these are an odd and even number. The only way to get these balanced is to multiply your N2 source by 3 and your nitrogen source on your reactant side by 2. All right, this will balance nitrogen and mess up everything else. And I've already seen that I've made a mistake with my oxygen because there's another 2 coming in from O2. So this changes oxygen's count to now 12 plus 2. Carbon now we have 14, hydrogen we have 10, and nitrogen we have 6. Oh, I'm sorry, over here. It's been a long day. 2 times 3 is 6, in case you were wondering. Yes, and Rin, you spotted it. It should be 6 plus 2 for our initial oxygen count. 100%. All right. Now, all right, so now we've got nitrogen balanced, oxygen's looking funky. I'm going to save that to the end. I'm going to do carbon next. I'm going to multiply CO2 by 14. This will balance carbon and change oxygen, because now we have 2 times 14 plus 1, so 28 plus 1. Next, I'm going to do hydrogen. We need 10 on the product side, so I'm going to multiply H2O by 5. So now we have 10 hydrogen and 28 plus 5 oxygen. All right, last element to balance here. We've got 12 plus 2 on our reactant side, 28 plus 5 on our product side. Now we need to multiply O2 by some number, so that 12 plus 2 times that number is equal to 28 plus 5. All right, which is 28 plus 5 is 33, right? So we're going to subtract 12 from both sides. And we're going to get, we're going to find that 2 times the number that we need to multiply O2 by is equal to 21. Divide both sides of this thing by 2. And we get a value for n. N is 21 halves. And when you multiply O2 by 21 halves, you'll notice 2 times 21 over 2 is 12 plus 21, which does indeed equal 33. Now, we know that we can't leave, we cannot leave a fraction in a balanced chemical equation, right? We've got to get rid of that denominator, right? Because we can only have integers in a balanced chemical equation. So we are going to multiply this entire thing. Oops. There we go. Multiply this whole thing by our denominator. So we're going to end up with 4 C7H5 N3O6 plus 21 molecules of O2, producing 28 molecules of carbon dioxide plus 10 molecules of water and 6 molecules of nitrogen. So this is the balanced chemical equation for the combustion of trinitrotoluene, or TNT. All right. So that is the business. Yes, Stephanie and Rin, you guys both caught. I messed up. The initial oxygen count on the reactant side is 8. But that is the balanced chemical equation that you can use to solve the rest of the TNT questions. All right, Rin. Or no, not Rin, sorry. Stephanie, you had a question. One of the balanced chemical equations on lab 4. Okay, let me... Yes. Well said. All right, let's see. Okay, hang on one second. I'm gonna pull up the lab for stuff. Let's see. Oh, hang on. Is it? Oh, it's over here. Okay, there. Sorry, Stephanie, it took me a minute to find these. Okay, hang on. Okay. Thank you for being patient. Okay, hang on. Any of the 4. Okay, So, Stephanie, quick question. So yeah, which balanced chemical equations in experiment 4 were you asking about, just out of curiosity? Okay, okay. So let me, because I'm looking at. Oh, okay, okay, hang on. That helps me out. All right, hang on one sec. Oh, okay, no worries, no worries. Okay. So, like, let me see. So, when. Oh, wait, hang on. Here we go. Okay. So, let's see, that's the data analysis, that's the ranking. So here's what the all of these are a class of reaction sometimes called a single. Oh, that's signal. So these are single displacements. Reactions. And as it says in the pre-lab, they follow the general form. You've got M plus AX, and they produce A plus MX, right? Where you can see that M has switched places with A. All right. Now, getting to like a specific example, like the one that you brought up, the reaction between lead, Pb, and copper 2 nitrate. So the products here, if you observe a reaction change, the products are going to be, so your A here is copper, right? And your M is Pb. So on the product side, you can see that A goes from being and X, I guess just for completeness, is NO3. All right, A goes from being in an ionic compound to being a solitary solid. So copper 2, right? Because this is right here. This is copper as a cation with a charge of positive 2. Becomes just copper metal. And then we're going to have plus MX, right? And the M, as we've identified, is PB. And it will also take on a charge of positive 2, because that's what we're dealing with here. And then nitrate, as we know, is a polyatomic ion, the charge of -1. So this gets paired with lead, and because lead is going to a positive 2 charge, we're going to need 2 nitrates to balance with its positive 2 charge. So this is what they want you to write, and you can see it follows the format for a single displacement reaction, but this is how you take that format with real reactants and kind of apply it to the situation. No such thing as a dumb question as long as it is honest. Let's see. Rin. Totally great question. Density is a ratio between the mass of a substance and the volume it occupies. And here's the deal. Is any volume unit is cool. Now, typically, you see grams per milliliters is probably the most common density you see in chemistry, but you'll see for gases, because they're not very dense, right? They're airy, they're light. Typically, the density of a gas is measured and reported in grams per liter. So they're both totally valid. They're just different units for the same quantity, which is density. Dude. You too. Hope you have an awesome night. Alrighty, it is 10 o'clock. I'm going to go ahead and call office hours for tonight. Thank you all for coming out and for just being kind and understanding today. It was awesome hanging out with you. I will see you all on Tuesday. No, I won't. But I will see you on Wednesday, lecture 1, and then office hours at